So today we're going to be introducing the concept of sine and cosine as actual functions that can be graphed. So I've set up on this document here a couple table of values that you guys can use. The front will be for the function sine x, and then you'll see on the back our function is cosx. So just as a little setup information for you, the x's, when we graph this as an actual function, the x's are going to be your degree values, and the y's will be the values as you rotate around the unit circle. So they'll actually be well, we know sine is y over r, so essentially it's giving us the ratio of the y over r components as these points go around our cast grid, that kind of idea. So the y components, we're going to be, of course, graphing on here. So this will be kind of like our f at x. And what I would like you guys to do for the y-axis is I would like you to go up by 0.25. So basically, this will be 0.25, 0.5, 0.75, and then this will be 1. And that's actually as far as you need to go with that one. And then on the negative part of this, we'll be going negative 0.25, negative 0.5, negative 0.75, and negative 1. Okay? You'll also see here that these are the x's in degrees. That was bad. Degrees. And you'll kind of notice here, I know it's like really small, but 3 ticks is 90 here. So what is 1 unit on the x-axis going by? 30s, yeah. So this is like 30, 60, 90, 120, and so on. So when you graph these, you're actually going to be going up. Each tick on the x-axis is actually each space in this table of values that I set up for you guys here. Okay, so what you guys are going to do is you can actually just use your calculator for this, and you're going to actually plug each of these x coordinates into sine x to get the value of f at x, and then you're going to plot the points and see what comes of that. Okay, and then you're going to do the exact same thing on the back for cosx, and you're going to see what comes of that too. Same scale on the y-axis. So I'm going to give you guys like 10 minutes to go through, fill in your table of values, and plot the points, okay? So that's what we're going to start with. So just to give you guys an idea here of what you should have got for the first set of points, as you plug into your calculator here, you should have gotten these points. Again, we're just making sure our calculator's in degree mode, and because this is the table of values for the function f at x equals sine x, as we can see at the top here. I'm plugging each of these degree values into sine x in my calculator, and we're seeing what we get out. This is generating x, y coordinates for us, x being the degrees, the x-axis, and these f at x coordinates being the y coordinates. So we're going to see what impact this has when we graph it on a graph where x's are degrees and y's are these f at x values. Okay, so see if you can get the graph of that. Okay guys, so I'm continuing from these points that I just showed you, and I have actually plotted the points here. So this is kind of what your graph should look like once you've plotted the points. And as we connect them here, you'll notice that they're going in kind of like an S shape. That wasn't great. So as we connect all of these, should end up with something that looks like this for your sine graph. Mine's a little squiggly, but you kind of get the idea here. So the important thing just to note for this is that my graph should look like it's curved and not in a V, like not pointed. So I'm just making sure that I curve around, especially those like 1 and -1 points, just so that it looks curved. But I think we can kind of see that it does form a curve there just based on how the points go. Okay, so How many of you guys have done the cosine ones? Everyone, pretty much? Okay. So if you're watching the, what's that? Yeah. Or you've done the points at least? Yeah. Okay, so if we jump over here, sorry, wrong file. Where's my blank one? Oh, it's this one. If we jump over here to the cosine points, this is what you should have got for each of those degree values for cosine. And then I'm just going to pause quickly here. You're going to try to graph it, graph each of those points. And again, if you're waiting, you're going to just work on filling in some of those extra spaces there, extending your graph in both directions. All right, so with these as our points, if we scroll down to our graph here, this is kind of what your points should have looked like. Oh, sorry, I have to unfreeze the screen for you guys. This is what your points should have looked like. And then when we connect these points, we have this. Okay, so again, just making sure that this is curved. And I also, if you happened to extend your graph in both directions here, you would have noticed that if I extend past 360, I'm essentially just adding 30s every time. So I'd be plugging in cos of 390, cos of 220, cos of 420, cos of 450. And you would have noticed that the graph continued in the downward direction. So did anybody get a chance to extend some of their graphs in some directions here? Okay. Yeah, so if we extend in both directions, what are some things that you guys ended up noticing about your graphs? Was there like any kind of pattern that was emerging? Yeah? So you would have actually noticed that it was essentially this. If I took this little section and copied and pasted it over here, that's essentially what you got if you extended backward into the 360 direction. So I'll just show you what I mean here. These ones are slightly different because the scale I used is bigger. But if you extended sine back into this direction, you would have noticed that the pattern was repeated again. So again, my x scale is a little bit bigger than your x scale in this one. But essentially what you should have noticed is that both of these functions are what we call periodic functions. Can someone remind us when we talk about a periodic function from Friday, what does that mean? Yeah, it has a repeating pattern over the same interval of x's. So from negative 360 to 0, I have the exact same repeating pattern of the y coordinates as I have from 0 to 360, and then 360 to 720 is going to have the exact same pattern again, and this pattern will actually continue forever. Okay, so that's kind of the idea. So your task after the lesson today is going to be, if you didn't get a chance to extend these guys in both directions, is going to be to extend sine and cosine to just fill up the graph. Okay? But just know for now that essentially this pattern continues forever in both directions, and same with the cosine graph. Okay? Any questions before we move forward to like analyzing these graphs? No? Okay. So if you want to hop over to your other sheet here, keep your graphs handy. Thank you. And what I'm going to have you do is just separate this into two sections, this part. And our first one will be for the graph of sine x. And our second one, maybe we'll call this g at x. We'll say g at x equals cos x. So we're going to take a look at some of the properties of the sine and cosine functions now. Okay, so domain of sine x. If we look over at our graph of sine x here, we discussed how we can kind of extend these. Is there any degree value where I would have to stop plugging that into sine? Like, is there any degree value that I'm not allowed to plug into sine? Or is this graph, if we think about this, is this going to extend forever toward the right and forever toward the left? Yeah, it's going to extend forever. I can plug in literally any value for sine as far as like the x coordinate degree value, and I should get a y value out. You can try it if you want. If you want to plug in the sine of 1 billion, you'll get a y coordinate out. So when we say domain, anyone remember? How do I say everything? Yeah, x is an element of real numbers. Okay, is cosine any different? Is there any like degree value that I can't plug into cosine? It will, that pattern will, if we think about it, extend forever, right? So that one is also all real numbers. Okay, range. This is going to be a little bit different. So if I imagine this pattern extending forever, maybe I'll use my one that's slightly extended. This is the graph of Sine X. What do you notice is like our bottom boundary and our top boundary here? Yeah, it goes from -1 all the way up to +1, but you'll notice that it will keep kind of oscillating between those two values. It doesn't go any higher than those. So how do I say that in an actual statement here? So for range, it's y, but yeah, we'll have that statement first. And then? So we'll do the lower one and then the higher one. We'll have a y. And which way? Is it lower point facing toward, or smaller point facing toward the left, or a bigger point facing toward the left? Bigger. So do I want to say this? So this is saying y is less than 1, but greater than 1. Or less than -1. Okay, so we want this way, right? So it's greater than -1, but less than +1. Perfect. Okay, how about cosine? If we look over, I'll use my other graph that's extended a little bit for cosine. But do we have any points that are going outside of that range? Oh, so it's the same as sine, right? Okay, so this one's going to be the same for range. Okay, period. Can someone remind us from our lesson on Friday what period means? The horizontal length of one cycle. Great. So if I look, I'm going to use this one again. If I look at my graph of sine here, I'm looking for the horizontal length of one section of this pattern before it starts repeating again. That's kind of what we said on Friday when we were introduced to the concept of a period. So let's just say, well, we can choose this as our starting point. This pattern is completely unique until we hit this point right here, and then the pattern starts repeating again. It goes back up into that mountain, and so on. So how long does that full cycle take? How many units would we say? So it's 12 units, but they're all 30 degrees each. So it takes a full 360 degrees. 360 degrees, and then it starts repeating again. How does that connect back to what we talked about last chapter? What's 360? Oh, it's a full rotation around a circle, and then if I keep rotating, it's the same points again, right? It's the same locations of all the arms again if I rotate further past a circle, past that one circle. So our period here for this function is 360, oops, should do it in red, degrees. Okay, so every 360 degrees, that pattern's going to start again. For cosine, is it different for cosine? Let's take a look. For cosine here, again, we can measure the period in many different ways. We can measure from a max to a max, or a min to a min. We can measure starting on the x-axis, wherever that starts, whatever. So sometimes I like to just start at the x-axis and then see when's the next time I hit this point again. So we'll see starting at that x-axis there, the pattern is completely unique until we hit this point right here, and then that pattern starts again. We see that? I mean, I can measure it from here to here as well. That's the same. But I think max to max, starting at 0, where does our last max end? What's that point? That point is 360, yeah. So again, the period is 360 for cosine. And that should make sense because one rotation around like that cast grid circle that we were talking about, and then once I get to 360, my arms are in the same place again. I get a bunch of other coterminal angles. Isabella? So for the basic sine and cosine functions, it's always 360, but we're going to do some transformations on these, and then it will change the period when we do transformations. Okay, and then amplitude, can someone remind us what amplitude was from Friday, Bonnie? Yeah, so essentially, actually, you're subtracted, yes. So if I do max minus min divided by 2, that should give me my amplitude. In plain English, the amplitude is half the height of the entire graph. So if I look at my graph for sine, we'll look over at this one. How many full units? I'm just talking about like 1, 2, 3. So I know that we've separated this out into like 4 pieces here, but this is 1 unit, right? That's 1. So how tall is my graph total? Well, this part is 1, but this part is also another full unit, right? So this is 2. So amplitude is half of that, which is 1. Okay? I can find this also by just locating my max and locating my min and doing max minus min divided by 2. So our max is 1, our min is -1. So if you want to calculate that way, you can definitely do that. You can do max minus min divided by 2, and we'll get 1 minus -1 divided by 2, which gives us 1. Okay, and then I think we can guess the max of cosine is also 1, and the min of cosine is also -1. So the amplitude of cosine will also be equal to 1. Okay, so those are some of the properties of our graph. If we happen to do some transformations to these functions, the amplitude could potentially change, the period could change, the range could change. The only time the domain would change is if we have like an application question where we're talking about time or something like that. And then, of course, we don't want to have negative time. So only in situations like that. So domain is, for these guys is always going to be all real numbers, unless we're talking about some kind of real life application where we can't have certain values. Yeah, so I want to just show you guys how this is related to what we talked about last chapter. Hopefully this link works for me. I thought you loved it. Up until a point, and then you hated it.
Yeah, at first it was really good, and then like it just went down.
Didn't like it from there? Oh, okay, hold on. Let me see if I can get this to... Let's just do this. Oh. Okay, here we go. All right, so oh, sorry. Okay, so I don't know why I can't see this whole thing. Let's do sine. I want you to see this, and then you can go, okay? Sorry, this is just loading. Here we go. And I wonder if I can change this to degrees. Maybe not. Okay, so just so you guys know, these right here, we learn about these in grade 12. But 90 is pi over 2, so this is 90, this is 180 pi, this is 270, and this is 360. Okay? Don't even worry about it. Yeah, don't worry about it. So if we kind of notice here, so this is my graph. This is kind of confusing, actually. I don't like this. Sorry about that little hiccup there. This is the one that I actually want to show you. So you will notice here that we have over on the left our cast grid that we know and love, right? Of course. And then we have here showing what we just graphed with sine, right? So you guys see it goes from -1 all the way up to +1. And the important thing to remember here is that sine, because sine is y over r, you guys remember how we separated our graphs into like the x, y, and r components last chapter? And we found that sine was y over r. What is radius of that unit circle that we talked about? Do you guys remember when we talked about the unit circle? I know radius is half a diameter, but when I say unit circle, do you guys remember back to that lesson we talked about a unit circle? What was special about the unit circle? What was the radius? Yeah, the radius was 1. So we're talking about a very basic circle with radius 1 here. And because radius is 1, sine ends up being, because it's y over r, sine ends up being y over 1. So sine just ends up being the y heights. So I want you guys to pay attention to the vertical heights as I travel around here. What is the vertical height of this point at the point 0? Is it higher or lower than the x-axis at all? Looking over on the left. It's 0, right? So it's not higher or lower than the x-axis, so it's 0. So as I travel upward, you'll notice that I'm going up above the x-axis, which is why my graph on the right over here tracks up to and toward the value exactly 1 unit above the x-axis. So if we look at this little portion over here, my point right now is 1 unit exactly above the y-axis, and that's why at 90, I'm up at the point 1. Okay? And then you'll just hold your questions until I'm done here, okay? And then, as I rotate over to 180 here, what's happening to the height of the point above the x-axis? What's it getting closer and closer to as we rotate around? It's getting closer and closer to 180. And is the point now above or below the x-axis at all? It's on the x-axis. So that's why that point at 180 goes back down to 0. And then, why would this section of the graph be going into the negatives here? Yeah, so I'm actually now here, I'm below the x-axis, and at 270, how many units am I exactly below the x-axis if this is a unit circle? Yeah, I'm -1. So here, for 270, I'm at -1 because I'm 1 unit below the x-axis. And then when we rotate back up to 360, we know that 0 and 360 are the exact same location. So now we're, again, at the x-axis, so we're not above or below it at all, which is why 360 has a value of 0. Does that answer your question, or do you still have a question?
Do we have to know why the graph relates to the circle for the test?
You don't need to, I'm not going to have you explain it, but it's good just to know in your mind. It will help you, it will just help your foundation and how this works, especially for next year. Okay, so cosine, guys, when we look at the graph of cosine, it's different than sine, right? So if you remember from what we did last year, is there something interesting going on out there? Not very interesting, I would say. Just kidding. So cosine, what do you guys remember as far as x, y, and r? How was cosine related to the x, y, and r components when we talked last chapter? What was cosine? X over r. And what is radius in the unit circle again? 1. So x over 1, that's just x. So cosine is tracking the horizontal here. So what I'm interested in is how far this point is out here to the left or to the right of the y-axis. So right now at 0, how far is my point away from the y-axis? It's 1 unit in the positive direction, right? Which is why at 0, I have a point up at 1. Okay, now as I curve around my graph from 0 toward 360, so going counterclockwise, we are headed to be exactly on the y-axis. So if we're on the y-axis at the point 90, That's why we're at 0. So we're not to the left or to the right of the y-axis at all. We're on the y-axis. So 90 is at 0. And then what's going to happen as I go toward the left here of the y-axis? What do you notice with the graph? It's going down into the negatives because now we're toward the left of the y-axis. So if I rotate all the way around here to 180, how many units am I now away from the y-axis? I'm 1 to the left, so now I'm at -1. So this point over here is 180, -1. And then rotating back toward the y-axis at 270, we're on the y-axis, so that's why 270 is 0. And then rotating back to our starting point at 360, we're now 1 unit over to the right of the y-axis, which is why 360 has the point 1. Does that make sense? Okay, so sine tracks the vertical position of the point, and cosine tracks the horizontal position of the point on the unit circle. Okay, so hopefully that helps ground the idea of where these functions come from and how it's related to what we did last chapter. If this confuses you, that's okay, but I think hopefully for some of you, you kind of see that connection. Okay? It's not super important that you understand that information. I mean, if you're continuing into advanced functions, you're going to want to have a good handle on that, but we kind of review it again next year a little bit. There's one other thing before we go forward with some of our like transformation information here. There's one other thing that I want you guys to do. So if you turn over to this sheet, we're going to actually be doing some transformations of the sine and cosine functions. But we're not going to use all of these points as our key points. There's some very specific points that we're actually going to use as our key points. So I want you guys to just highlight them if you're able. We're going to use, it's going to be, oh no, sorry. Hopefully this will work, maybe. No. Okay, I'll do it like this then. We'll just circle them. This is going to be a key point. This guy is going to be a key point. This guy, this one, and this one. Why did I choose 0, 90, 180, 270, 360?
Those are the 4 points.
Yeah, those are the 4 things on the outside of our cast quadrant, right? So if I can remember this, I don't have to memorize the y's, right? How can I get the y's if I just know 0, 90, 180, 270, 360? We'll just plug them into the sine function. So I don't have to memorize them, but these 5 things are going to be, once we start doing transformations, they'll be our key points of Sine X. Okay? So if I can remember 0, 90, 180, 270, 360, I can get my key points for sine and cosine. Okay, and then for the cosine graph, I'm going to circle the same points, 0, 90, 180, 270, 360, and the y-coordinates are slightly different for those. So those will be the key points of cosx. Okay. If you want to, you could use all of those as your key points. It just gives you more points, but it's just going to be more time consuming to transform all of those. Nicole?
Just out of curiosity, is there a way to know like how long, like or what numbers the period is, or do you just have to figure it out by seeing what number it is?
Yeah, so you'll notice with your y-coordinates here, the numbers don't start repeating exactly until you go past 360. So you'll notice that when you do 360 to 720, you'll get exactly these y-coordinates repeated in the exact same order again.
Is there a way to know it besides checking any number and seeing what
The period's 360, we just discussed that, right? So you can just know that the period's 360, and then if transformations happen, then we'll kind of talk about how you can figure out that period without having to do all of the points. Yeah. Okay, Joey?
Are the key points of cosine the same as sine?
The x's are, but the y's are different.
Okay.
Yeah. Okay, so you guys should make an observation as well here. Do you guys notice how sine and cosine are really similar? But one is kind of just like a shifted version of the other one, right? So if we notice where the max is on cosine here, our max of sine is 90 degrees over to the right. So they're just like slightly different shifted versions of one another. Okay, Natalie? Not in this course, no. If you want to, you could graph it just to see what happens. It's very interesting. You're good? You don't want to? You don't want to spend your night doing that tonight? No? Okay. Okay, so I am going to just remind you guys about our A, K, D, and C values for transformations. They also have a graph feature when we're talking about waves. These are called sinusoidal functions, these wave functions. So both the sine and the cosine graph, they're called sinusoidal functions. It's a fun word. Okay, and then I'm going to tell you what each the A, K, D, and C do to your graph. We'll remind you about the transformations and then also about what we call the graph feature of these sinusoidal functions. So A, the A value is our vertical stretch compression or flip, right? We know that. So same transformations as we've done in our past units, in our transformations unit and exponentials. This also tells us an additional graph feature, and the additional graph feature is if I do the absolute value of A, it actually gives me the amplitude of the graph. What does absolute value do? Can you guys remember? Does anybody know? No one's seen absolute value before? No. Absolute value just makes all numbers positive. So you guys remember on Friday when we talked about how you can't have a negative amplitude? Because it's actually talking about the height of your graph. It's half the height of your graph. So absolute value just makes all numbers positive. Okay, and the only reason that we need to do that is just, again, because we want to make sure that we don't talk about a length of a graph or a height of a graph in terms of like negative values. It doesn't make sense if I say Isabella is negative 180 centimeters, right? Does not make sense. What? Exactly. Maybe. But for the most part, it doesn't make sense, right? Nicole? The amplitude is still talking about the number of units, like half the number of units from max to min. So still would not be negative. Yeah. Okay. K value. Does anyone remember what this does back from transformations? It's horizontal. Very good. And this is also a horizontal stretch compression flip. And the K value can actually, this is what Nicole was asking me, the K value helps us find the period because the K value is a horizontal stretch or compression. So it's directly related to if I stretch in the horizontal direction, I'm actually stretching the period. I'm stretching the length of a cycle, right? And if I compress in the horizontal direction, I'm actually taking that period from 0 to 360 and I'm compressing it. So I can calculate the period by doing 360 over the absolute value of K. Or I can rearrange this formula and I can get the K value by doing 360 divided by the period if needed. Okay, depending on what information I have. So I'm taking 360 and I'm actually like considering what the stretch and compression factor is and how that changes the period. Okay, D value, we know this shifts left and right. So if it's positive, remember it looks negative in the equation. And this will shift our graph right shift. And if the D value is negative, it will look positive in the equation. And it will be a left shift. As far as graph feature, we usually call this a phase shift. That's what it's called. A fun word to say that we're shifting a sinusoidal function. So we call it phase shift. And you can basically just say like phase shift 90 degrees right, or phase shift 45 degrees left, whatever. Okay, and then C value. C value is very straightforward. When it's positive, come on, purple. There we go. When it's positive, this will be a shift up. When it's negative, this will be a shift down. And in terms of sinusoidal functions, we call this vertical displacement. Okay, so essentially vertical displacement up 1, vertical displacement down 1. Okay, so everything same as usual, but we are just going to work on some of our new stuff here, which is amplitude, the period, the phase shift, vertical shift, just to make sure that we can identify those. But just know that the A, K, D, and C values, if we're talking about the actual transformation itself, they do the same things as before. They just tell us a little bit more information about our graph. Okay, so here I would like us to just fill in some of our, this can be shift or displacement. I would like us to fill in some of our information here. So amplitude. Can somebody tell us what the amplitude would be here?
How do you find the absolute value?
So if it's positive 3, it will remain positive when I take the absolute value. If it's negative 3, it will become positive when I take the absolute value. So what's the absolute value of 3? 3. Yeah, that's right. Okay, so that's our amplitude. Period. So I can calculate the period by doing 360 over absolute value of k, which is 2 here. So this is k. So essentially I just get 180 degrees. Okay, so if we think about a k value of 2, can somebody tell me in words what this transformation actually does? K, when k is 2. It's a horizontal compression by a half. So do you notice how the period now has been halved? So if I took my graph and I compressed it horizontally, that means what used to fit between 0 and 360 actually now fits between 0 and 180. So it takes half the time to complete a full cycle. Does that make sense? Perfect. Okay, somebody tell me what my phase shift is. 60. I need more though. 60 degrees, Bonnie, to the left. Okay, remember this looks opposite of what it actually is in your equation. Okay, and then my vertical shift or vertical displacement. Anyone give us that one? Okay, yeah, so that one is down 1. This one is just a unit. We'll just call it unit. So the x's are degrees, the y's are just like the ratio values. Okay, max and min. So if I know the amplitude, actually I'm going to have you guys add on to this as well. The C value is actually the middle of our graph. And this is important for finding the max and min. So if I know the C value, I know that my max from that value should be equal to the number of units to get from that value to the min. So the distance from the C to the max and the C to the min is actually the equal. So when I think about a wave function like so, My C value will actually be this very center line that separates the mountain from the valley. And then these distances from the C value to the max and the C value to the min are actually equal. Okay, so like C to the max is equal to the number of units from C to the min. Okay, and I'm not talking about like direction or anything here. I'm just talking about like number of units that fits between those two values. Okay, and that just so happens to be, if I calculate C to the max and C to the min, those values happen to be my amplitude value, right? The amplitude is half the height of the graph. So if I'm tracking C to the max and C to the min, I'm actually finding that amplitude value of my graph. So here's the deal. If I know the amplitude, I know the distance from C to the max, and I know the distance from C to the min, it's the amplitude. So if I know the C value, and I know the amplitude, I should be able to get max and min. So I usually like to just draw myself out a picture here. And I'll just draw like a little hill, just like I did in the last one. And I know that this C value, my middle value, is -1. And up to the max is going to be 3 units. And down to the min will also be 3 units. So where is my max? If I count 3 units up from -1, where will I be? 2, right? So if I count up 1 unit, I'm at 0, and then if I count up 2 units, I'm at 1, and 3 units, I'm at 2. So the max is actually at 2. And then if I count down 3 units from -1, where will I be? That's right. You got it. Okay? Just a little tip, guys. Your max should be higher than your min. I know. So if you happen to get the reverse, maybe you calculated them wrong. Yep. Yep. Okay, so I want you guys to try the one below. Everything can be calculated the same. Doesn't matter if we switch from a sine to a cosine function, and see what you can fill in. And then I will fill them in a couple seconds. So this is our question. If you're watching the video, you can just pause it and try it out. I'll just zoom out a little bit here. There we go. So that's the one we're going to try. All right, I'm going to start filling in my answers. You can check once you're done. All right, so I got 2 as my amplitude. So remember, when we talk about, even though this is a vertical flip, when we talk about amplitude, we want to talk about it as a positive because it's a length, or a height rather. Period. So you guys may have noticed that there was no visible k value in here. If k is not there, we assume there's no horizontal stretch or compression or flip, and we can just, I mean, the period is unchanged, but if you wanted to calculate it, it's essentially 360 divided by 1 as your k value. So if we don't see the a or k, that means they're 1. Phase shift 30 to the right. Remember, it looks negative in here, but it's actually positive. And then up 5 units. Over here, I just drew you guys a little picture. So C is the middle of your graph. If I count up the amplitude from C, I'll get the max. If I count down the amplitude from C, I'll get the min. So what did you guys get as your max and mins? 7, yep. Not quite. Just down 2 units from 5. So positive 3, right? Yep. good. Any questions on this? We're all good? Okay.